Hi, I'm Kevin Keller, the pragmatic statistician. In several episodes of Street Stats, you have heard me say higher R squared is not the objective. A useful model is the objective. In my correlation video, I talked about the strength of correlation, but I was not obsessed with higher R squared determining goodness of fit or the magnitude of R squared determining a relationship. This episode today is hopefully going to give you more context that higher R squared is not always the goal. In fact, it should never be the goal. A useful model is always the goal. So just like the song says, let's start at the very beginning. Now, last time you'll hear me sing. All right. So back in high school algebra, you learned that if you had an xy coordinate plus another xy coordinate, you could draw a straight line between those 2 points. And then your algebra teacher taught you about a formula y is equal to mx plus b, where m is the slope and b is the y-intercept. So we learned that in high school algebra. Now, if you happen to teach statistics, almost all of us use this as a gateway to teaching about simple linear regression. Only there is no such thing in the real world as a perfect relationship, like you learned in algebra. The streets are messy, and so is data. Variation exists, so you use algebra as a gateway to teaching regression and coming up with a model. So, in our case, we come up with y is equal to b sub 0 plus b sub 1 times x, where b sub 1 is the slope and b sub 0 is the y-intercept. You go, why did we switch things around? It becomes evident in multiple linear regression why we did that. We'll talk about that one other day. You ultimately get to the concept of least squares. The line is fitted such that the variation between the points and the line is minimized. Back in the days of dinosaurs, we used to have to do that all by hand, but now the computers do it for us. Ultimately, you learned about the correlation coefficient, R, and then R squared, how much variation was explained by the model. All of this teaching was great. Very sound logic, sound teaching. But then either the teaching went off the rails or your understanding of the teaching went off the rails. You took away higher is better. And whether you have a good model or not is based upon that magnitude of that value. If you believe that a high R squared means you have a good model and a low R squared means you don't have a good model, then time to shake up that Etch-a-Sketch board and start to reprogram. Etch-a-Sketch boards all shaken, ready for reprogramming? So we're going to start with a very simple concept. Whether you have had an economics class in school or not, you understand the concept of price elasticity. In very simple terms, if a product is elastic, then as the price of that item increases, sales goes down. You buy less. If it is inelastic, then no matter what the price does, you continue to buy the same amount. Now, pick your favorite product you might think is elastic or price sensitive. Snack foods, eggs this year, soda, beer, cookies, whatever you want. Now, for purposes of this episode, we're going to assume that that relationship is linear. In this case, you'll see shortly the slope is -2 through the price range in our example. Now, it's definitely not linear in the real world, but we're going to keep it simple for now. And we are assuming through cause and effect, price goes up, sales goes down. Cause and effect is real. Right, so let's look at this example. So I created a relationship. Y are sales is equal to a minus X or price plus 100. So we've got a slope of -2, y-intercept of 100. If our price went down to 0 and it was linear throughout, we won't get into all that. You know that. But our R squared is 100%, correlation coefficient of a -1. This is a perfect relationship. This is what management always wants in every model we generate. But that's not reality, and you know that, and even management knows that. So what I did was I created a bit of variation, a bit of random noise. So you'll notice that I have all of this data incremented in dimes. So we go from $15 to $15.10 and so on up through $19. To each of those sales, I introduced a small amount of random noise that's normally distributed purely at random, and I generated enough random noise to get me to a R squared of 95%. You can see the correlation coefficient, negative 0.976. And so you can see that the relationship is pretty strong. Notice the slope has gone from a -2 to a -1.847. If we generate a confidence interval, we're going to likely find that -2 falls within the confidence interval, but it's entirely possible to get a slope that is above or below a -2. So then I increase the variation a bit more. There is not an underlying variable to any of the rest of this data. It's pure random noise. The relationship still exists as price goes up, sales goes down, but the world is messy. So now we have a correlation coefficient of 0.9, 82%, rounding error. Then I did that to get something close to 70% R squared, negative 0.856. And then I got it down to 64%, a correlation of a negative 798. And here we're at a correlation coefficient of a negative zero point 0.7. And if you saw my correlation video, you know that I said this is the start of a strong relationship. And then I made a big point about R squared of 49%. There is a clear signal in that data. It's statistically significant. In this case, the slope is way above 2 or -2, but it's still within the possibility that's just happened through random noise. The signal still is real, just random noise around that. This is why statisticians and great instructors will say just because you get a statistically significant signal doesn't necessarily mean it's cause and effect. You've got to go study it. Is it really cause and effect? And of course, in this case, it is. So then I took it down. I got a correlation coefficient of negative 0.43, which is right at the threshold of what I would call a moderate. And again, we have a slope of a negative 1.6. So the relationship is still there, but it's getting masked by all of the noise. All right. So hopefully that's helpful in understanding when a signal is real, how random noise can start attempting to mask that. It doesn't diminish that the signal is real. So, did our underlying model change? The answer is no. Our product is still elastic. As price goes up, sales goes down. But there's a lot of noise. Some of that noise could be actual variables that we haven't accounted for in a real world problem. Some could be confounded with other things going on that we aren't measuring. So typically, we do regression modeling on extremely messy data. We have to reprogram our minds. We are panning for gold. We are not walking into a mine where the walls are coated with gold. That just doesn't happen in the real world. But our management expects the world to be perfectly predictable. It simply is not. Let me give you a really simple example. My wife and I will go out to dinner, and before we leave, we're going to our favorite Mexican restaurant. And so we're driving down the road, and it's about a 15-minute drive. And all of a sudden, she'll see another restaurant. She goes, "You know what? I've changed my mind. Let's go here." And so we do. Now, what happened in that moment is that particular restaurant sales went up a little bit for no other reason than my wife changed her mind. Model worthy or purely random? I would suggest that it's noise. Now, not my wife, but our influence on the sales of that restaurant and the lack of sales on the restaurant we were going to. Noise is pervasive in the business world. It's everywhere in our historical data. Higher R squared is not the pursuit. Now, there are four bad outcomes with higher R squared is better mentality. The first one is the least. From a technical perspective, R squared does not determine whether a model is good or not. Residual analysis, and you learned that in class. Residual analysis tells us whether the model meets the assumptions of goodness. Now, you might have been answering emails during that time, but you were taught that. In the grand scheme of things, this one is quite minor. Out of hand, you reject a signal because the R squared is low. That could be a real signal, and you just walked away from knowledge because it wasn't a silver bullet. Silver bullets show up in with higher R squareds. Silver bullets in the real world are rare. Number three, statisticians and statistical software provide you with ways to decide which model should I choose. I use several of those approaches, but I always perform my stepwise process manually. I do it step by step where I'm in control of what models go in or what variables go in and what variables leave my model. Remember our old friend George Box. All models are wrong, but some are useful. I do not need a model with a high R squared if it isn't a useful model. Develop models not only with statistical significance in mind, but more importantly, with business and common sense approach. And finally, and most importantly, the obsession of trying to explain every last ounce of variation will lead to overfitting of the model every single time. You get that high R squared, but the model is worthless to predict what will happen next. And if you plug in new data points, they'll be way off. You overfitted your data because the goal was a higher R squared. Let's think about my wife and I changing our minds going down the road for dinner. You could have a variable in your model that accounts for that source of variation, but it's not reliable in the future because other things will happen. You are in the game of statistical whack a mole in attempting to explain every source of variability. Not sure which is actually worse, creating an overfitted model or missing a signal, but either are bad. So the upshot: analyze your data. If you get a statistically significant signal, dig in further. Actually test for it if you can. If you can't test for it, and there are times you can't, what are the underlying assumptions that would explain cause and effect? Is it really cause and effect? If so, you now have a useful model that you can base business decisions on. So be careful out there. The streets are messy and so is data. But remember, there's always a way.